Brought to you by Chevrolet. Find new roads. We're here today to take a very special look at the game we know and love from a bit of a different angle. Today we have on the show a guest baseball theoretician, Michael Brennan. We're going to see about that later. But for now, we'd like to take you behind the scenes on Michael's new book, Physics in Baseball. And we're going to take a look at how physics impacts the game of baseball. For demonstration purposes, we have a video sent to us straight by the Baseball Federation of America. Let's take a look at what they've sent. That was an example of Newton's three laws. Let's take a closer look at exactly what happened when that player hit the ball in this segment, taking a closer look. The first law, the law of inertia, states that objects at rest remain at rest, and objects in motion remain at constant velocity unless acted on by an external force. That under the same principle, objects will have inertia, or a tendency to resist a change in its motion. Inertia will have a direct relationship with the object's mass. In this clip, Michael hits a small, very light ball, but once the ball is struck, we can see how the ball accelerates and begins to move off the tee. Because of drag or air resistance, a form of friction, and the force of gravity pulling downwards, the ball will face pushback in the x direction, get pulled down in the y, but without these external forces acting, the ball would continue traveling with constant velocity. What is acceleration? Acceleration is the change in velocity over time represented by a unit of distance over a unit of time squared. Acceleration, like velocity and displacement, is a vector quantity and takes into account changes in direction. In the case of Michael swinging the bat to hit the ball, the bat experiences centripetal acceleration even if the speed at which the bat moves is constant, because the bat continuously changes direction as it moves in the circular path. Positive or negative acceleration does not directly indicate if an object is speeding up or slowing down. Accelerating in the negative direction when an object already has negative velocity will increase the magnitude of its velocity in the negative direction. Acceleration can be represented in an acceleration time graph, or commonly as the slope in a velocity time graph. Newton's second law is an equation which uses acceleration. Force equals mass times acceleration. An object's mass, unlike its weight, is its quantity of matter and will be constant. Given this, as seen in the equation, if Michael hit the ball with the greater centripetal force, the ball would experience greater acceleration. A ball with less mass, like a baseball, is also faster to accelerate than, say, a ball with more mass, like a bowling ball. Seen by the equation, the force will also act in the same direction as an object's acceleration. So, in the case of Michael swinging the bat, we know that he has both centripetal acceleration and centripetal force, and that the force of tension in his muscles pulls inwards to the center of his rotation or his body. Newton's third law. A force exerted by one object on another, a force of equal magnitude in opposite direction, is exerted back. In the diagram, a finger pushing on a wall receives pushback as force normal from the wall on the finger. Clearly, the force of one is the same type of force as the one on the other. When Michael hits and exerts force normal on the ball exerts an equal force back onto Michael. Michael experiences friction from the ground and his body is held in place, whereas the ball has no such support and is sent flying in the other direction. Our studio's got linked up now with Michael J. Brennan, author of Physics in Baseball, here to talk to us now about projectile motion. Michael, what's going on? Can you hear us over there? How are you doing?
Thanks, Max. I'm glad to be here.
I understand we have another video from the American Federation of Baseball. We're going to show that clip now.
Projectile motion is the two-dimensional motion of an object. In the case of baseball during its flight, it is moving in two directions, in the y direction and the x direction. So important things to note about projectile motion are that the acceleration in the y direction is always negative 9.8 meters per second, and that there is no acceleration in the x direction because the x component of the velocity is always constant. During projectile motion, an object always takes a parabolic shape during its flight, and at its maximum height, its y component of the velocity is 0. Now, after some calculations, I've determined the time of flight to be 2.8 meters per second, the x component of the velocity to be 24.3 meters per second, and the displacement being 65.1 meters per second. However, when I use the equation x final equals x initial plus the x component of the velocity times time, I get 68.1 meters per second. But why are these values different? And the reason why is because of air resistance, which is a type of frictional force. And the force of friction is the force that acts against the motion of an object. And we can see in this free body diagram that the force applied, the direction in which the ball is going, and the force of kinetic friction is going the opposite direction. Force of friction can be defined through this equation, which is mu, or the coefficient of friction, times the force normal, which can equal mu times mass times g, which is 9.8 meters per second. And if we assume that mu equal between the baseball and the turf is 0.5, with the mass of the baseball being 0.14 kilograms and g equaling 9.8 meters per second, we can calculate the force of kinetic friction as being 0.68 newtons.
Wow, thanks, Michael. But hold on a second. I'm hearing a lot of talk about displacement and vectors. Can you go over what these things are for us?
Displacement is the straight line distance between 2 points. For example, when I hit the ball, the distance between where it first was and where it landed was 65.1 meters, so therefore that's displacement. However, it is important to stress that displacement and distance are not the same thing. Displacement has magnitude and direction, while distance only has magnitude. To put this more clearly, let's assume that I run from first to third on a baseball field. My distance that I cover would be 54.8 meters, because that's how far I ran. However, my displacement, which would be from first to third, would be 38.8 meters, because that's the distance between first and third. Now, it is also important when talking about something like this to explain vectors. Now, vectors also have x and y components. And to think of this more clearly, let's pretend that we are talking about a right triangle, okay? If we look at this right triangle, we can calculate the y component as being the vector times the sine theta, because this leg is opposite of the angle we are trying to measure, and sine is the opposite over the hypotenuse. And the same can be said for the x component. It can be described as being the vector times the cosine of the angle, since cosine is the adjacent over the hypotenuse. And if we want to check our value, we can use the Pythagorean theorem.
That's great, Michael. But before we finish today's episode, let's review two more important concepts if we want to understand what's happening in this footage, another clip from the American Baseball Federation. What is weight? Contrary to popular misconception, weight is different from mass. Mass, a measure of matter in an object, or you can say a measurement of an object's inertia, is constant of an object, whereas weight is actually a type of force acting on an object due to gravity, the Fg. As seen in this free body diagram of the ball, the force of gravity pulls down on the ball as it sits on the tee. For this reason, weight is not measured in kilograms, but in newtons, because it's a force. On a flat surface, or when an object is in free fall, the impact of gravity is easy to find by multiplying the object's mass with the planet's gravitational constant. In this example, the ball has a mass of 0.4 kilograms, multiplied by 9.8 meters per second squared, gives about 1.37 newtons. Weight changes depending on the influence of gravity. On the moon, where g is about 1/6 of what it is on Earth, 0.14 times 1.625 gives only about 0.2 newtons, so the weight of the ball would be much less on the moon, or a planet with less gravitational force. One last topic, what is the force normal? The force normal is a contact force between two solid objects, preventing them from passing through one another. When two objects are not in contact, such as the ball and the ground, when the ball is flying through the air, Fn equals 0. It's easy to imagine that as the ball rests on the tee simply supports the ball without exerting a force back. But if this were the case, the ball would actually accelerate downwards as the force of gravity, its weight, pulls it towards the earth. On a flat surface as such, where the floor supports the object so that there's no vertical acceleration, Newton's second law can be rewritten to solve for Fn. Essentially, whatever value will counteract the force of gravity, here solving for weight, 0.14 times 9.8 is 1.37, newtons must also be the normal force pushing back on the object. A stronger normal force will also indicate a stronger force of friction, visible in the formula Ff equals Fn times mu,